I'm also going to just. Okay, so we're going to start the recording now. I know, we're excited. So my name is Nicholas Crouch. I work in the Maths Learning Centre here at the University of Adelaide. So I've had a bit of experience with the Maths for Economists course over the years. Yupping's been doing a great job for the last few years. So this is where we're going to talk about some topics related to what you might see in the exam. And it's about you guys asking me, this is where you get a chance to ask questions, all right? So when we talk about proof by induction, so I'm going to start by talking about a bit about proof by induction, can be a bit difficult to make these things up from the top of your head. But induction follows a fairly set pattern, all right? So there's always the base case, and then there's the inductive step, and then we kind of bring it all together. So one of the things I know you can prove by induction is that the sum of I squared from I is equal to 1 to n is equal to n plus 1 to n plus 1. Oh, right, sure, 1, 6. Okay, so the base case for this is, n equals 1. And so that sum is like I is equal to 1 to 1 of I squared is just going to be 1 squared, which is equal to 1. So that's one side of this equation. If n is equal to 1, I've got, so n plus 1 to n plus 1 on 6 becomes 1 times by 2 times by 3 on 6, which conveniently is 1. And so 2 for n equals 1. All right. Sometimes I'm going to digress a little bit and go, actually, we're going to define a proposition. Pn, the proposition so sometimes we do this because it's easier to talk about a proposition. All right, so we've got a proposition that is a statement that is dependent on n, so it's a little bit like a function in some respects, but it's a statement that involves n. Let's put that back up. And so I want to be able to talk about it. So we have shown P1 is true. All right. So a proposition is a statement that has a true or false value. In this case, we've defined it in terms of some number n, and so for each n, it can have a different. It can be true or false. Awesome. Okay. So with this sort of thing, what we're going to do, the process is fairly standard, right? So we're going to assume Pk is true for some k. I'd like to actually go that is, and so we're going to actually be specific about what we're saying here, all right? And this is actually one of the key parts about doing this, is we want to be specific about what it is we're saying and what it is we want to prove, all right? So I'm saying that, okay? Now, we are going to go consider. Consider. How about I put all the letters in? Sounds like a great plan. If I go I is equal to 1 to k of I squared, and then I plus k plus 1 squared. All right, sounds like a crazy plan. What are you doing? So the plan is going to be then that I go, actually, what this means is I can write this sum as some I is equal to 1 to k plus 1 of I squared, saying the same thing. By assumption. We're going to say this is equal to this, k plus 1, 2k plus 1 on 6 plus k plus 1 whole squared. All right. Love the plan. So I'm actually connecting sort of the left side of this, the proposition we're trying to prove with the right side. And so I've assumed this to be true for this part, and I've just added this part. So I'm going back, I'm basically copying this, but I'm sort of going, hang on, that's equal to that, but that would be, by my assumption, that would be what that is. And then this is going to be, and that's the extra term that I'm adding. Now, I am going to do a funky thing where I go k plus 1. So I've taken k plus 1 out of here and ak plus 1 out of here. So I'm going to have k, 2k plus 1 on 6 plus, and this is a k plus 1. And I'm going to go on 6 and I'm going to times by 6 to create a common denominator. All right. This is just, at this point in time, hopefully this is just algebra. I say hopefully because we need it to fall out yet, but we're going to work out what that is. All right, so I've got a k plus 1. One of the other secrets about what I'm doing is I'm actually trying to avoid expanding this all out because I want to factorize it in the end. So I don't want to expand it all out. All right, now you see I've taken the on 6 part because they're both fractions on 6, and so I can just work with this numerator. So I'm going to have 2k squared plus k, and this bit is going to get me plus 6k plus 6. Who knows? And so I'm going to say this is equal to k plus 1 on 6. And this bit is 2k squared plus 7k plus 6. Now, by the magic of knowing stuff, I'm going to go, this is going to be a 2k and a something and a k and a something. And if I think of two numbers that multiply together to give me 6, that would be I want a 3 there, don't I? I do 3 there and a 2 there and make them both positive. Sweet. That's going to get me my 2k squared. 3k plus 4k is 7k. That's going to be right. So I can actually then go this little bit where I kind of go, hey, I can factorize it. I'm allowed to do a little bit extra on the side just to sort of, work out what's going on. And so I said 2k plus 3, and then k plus 2. All right. Now, I'm going to be a little bit bloody-minded about this, k plus 1. And then this is I'm going to write as k plus 1 plus 1. And this one I'm going to write as 2k, 2 by k plus 1 plus 1. Now, the reason I've done this is this says this is the right-hand side. The right-hand side of our proposition. So therefore, if P of k is true, P of k plus 1 is true. All right. So, since P1 is true, the thing we started off by showing, and pk plus 1 is true if pk is true, by principle greater than or equal to 1. Whoops, we didn't go there. All right, so with induction proofs, they kind of follow the same thing. I've made this so that this is exactly this where I've replaced k by k plus 1, because I've replaced k by k plus 1 in this sum. And so I've written it like that very specifically so that I can recognize it fits the pattern for the proposition k plus 1. Okay, kind of important that I make that quite clear at this point in time. That's the thing that I've done to work this thing out. Did you, sorry, every so often I do this, which is not necessarily great, but I interpret that look on someone's face that says, I didn't follow what you did there, Nick. All right, that is correct. Okay, let's talk about it. So we're okay with what happened sort of here. So here I started with my thing that I assumed to be true. So that thing I assumed to be true. If you imagine I'm adding this to both sides, all right? So I sort of added it here and said, hey, that's going to be this thing. And if I add it here, that's going to be this. But then I've noticed that this has got a k plus 1 and this is k plus 1 times k plus 1. I've taken that out as a common factor. Okay, so when I take that out of here, I've got k, 2k plus 1 on 6. This one, k plus 1, because there was 2 of them. And then I've times by 6 on 6 to make it so I have a common denominator. That common denominator I've pulled out the front here. All right, and I've just expanded out what's left. 2k squared, k, 6k plus 6. Simplified that. I kind of know that it's got to be equal to this, but I've actually sort of worked out the factorization of that quadratic here. I could have used a quadratic formula to solve that for me if I wanted, if I was having trouble with that factorization. So that's always a possibility because, you know, this is not obvious factor. This is a non-trivial sort of way to see that factorization. It can be quite difficult. Now, and then we've got this sort of thing. So that's one particular type of proof for this thing. All right. So induction is almost like induction can be one of the easier types of proof because it has a form, has a fairly rigid structure that we're putting in. You know, we've made an assumption about case 1, we've shown the first case, we've made an assumption about some arbitrary case. We then show the next case is true. And then we're just a matter of going, hey, I've got this thing that says principle of mathematical induction. If I can show that it's true at some point, and that if at some point it's true, then the next case is true based on that, then I can say that it's going to be true for all k. All right. So that's kind of a fun one to do. It's very similar to what I think showed you in your lectures. I made it simpler, all right, because the thing you are likely to see in your exam is like that, but is probably no more complicated than that. All right, there's a lot of things I could do, but I don't want to make it too complicated because that's going to sort of disguise what's going on. All right, so now one of the unfortunate things here is I'm trying to work out what other types of proof you've been given. Vector spaces, I did vector space stuff. Wasn't prepared enough. The system of linear equations, okay, that's all good. We can sort of anything from that. What I want to see is what you've said about matrix stuff. There's one variable. Oh, you didn't limit definitions. Okay. Possibly where we want to do. I'm going to go back. I'm going to just check and see what other types of mathematical proof you've done, because that can actually be quite important to There's a couple of other types of proof. If I talked about contrapositive, have you heard the term contrapositive? No, that's what I want. That's actually what I wanted to know. Because that's a very specific thing. And if you had heard of it, I would want to be doing it. Integrated differential. Yep. Contrapositive is, so this is your proof by mathematical induction. Prove induction that. Sure, I could do that. Proof by contradiction. Irrational. What else could we prove by contradiction? I mean, like literally the two classic ones are, so there are infinitely many primes and root 2 is irrational. I'm trying to, the problem with trying to come up with these things off the top of your head is it can be very difficult to come up with something that's got something. Let's check this one. It's actually quite, like, if you look at what you cover in this course, you cover a lot of things. And so it can be difficult to talk about all of the things you cover. I didn't bring something that I wasn't expecting that one. No, okay, gonna give it up. You talked about, so you did talk about sequence stuff. What's that? Sequence stuff.
Oh, sequences.
Yeah. You had, so I noticed somewhere in the lectures, was it this one? Yeah. So a lot of this stuff about domain, range, codomain, sort of is just introducing terminology, utility function, logs and exponentials. So there's a lot of these rules that you sort of, if you're good with your mathematics, you can do. That's a challenge one to, I don't remember the proof of that one off the top of my head. So what is it? We could actually do, let's go here. We could try. And then four. I think that's right. Yeah, that's right. So this is actually, I'm going to give this one a go. See if we can't do this one. So proposition 2 to the n greater than n squared. And that would be another induction. All right, that would be what I'd be thinking of doing. All right, so if you actually look at this, 2 to the 1 is actually greater than 1 squared. 2 to the 2 is greater than 2 to the 2. That's not true. 2 to the 3 greater than 3 to the 2. Also not true. 2 to the 4 greater than 4 to the 2. They're equal. And so when we get down to 2 to the 5 greater than 5 squared, that would be true. All right. This is kind of fun. Okay, so P of 5. P of 5 would be our first case, and we are going to go that is 2 to the 5 greater than 5 to the 2. 2 to the 5 is equal to 32. 5 to the power 2 is equal to 25. And it's true. All right. One of the things that can actually make it quite difficult is actually when we're talking about inequalities, the inequalities themselves can be difficult to work out what I'm going to say. Okay, so that's where we're going. All right, so so we're going to assume PK is true, and we're going to state what that is. So I go, that is 2 to the k greater than k to the power 2. All right. We are loving this plan so far. I'm going to have 2 to the 2 to the k, and I'm going to say that's greater than 2 to the k squared. Sure. Now, this bit here is going to be 2 to the k plus 1. That's actually the thing I want. I want the next case to that side. All right. This, I'm actually going to write this as k squared plus k squared. All right. Yes. Oh. I'm really good for that. Make sure you remember to tell me if I've done something stupid. It's really good to be reminded that I'm not showing you what I've got. Now, remember here that k greater than or greater than 4. So I really want to show this is greater than. So if I go, I'm off the side here, I'm going to go k plus 1 whole squared. That's going to be equal to k squared plus 2k plus 1. All right. Ideally, what I want to show, all right, so this can be an interesting thing to do. If I want to show, so I've brought it down a little bit. I actually want to show k squared is got to be greater than 2k, well, greater than or equal to plus 1. All right. And just a little bit, so like, if I did this, if 1, this would be 3. So k is equal to 1, k is equal to 2, that's going to be 4, and that's going to be 5. That would be 9. This would be 7. This actually doesn't become true until k is equal to 3. All right. But we're dealing with where my proposition doesn't start until n is equal to n is greater than 4. So I'm actually going to be all right. So what I'm going to do is to show this thing here. So I'm actually showing this is going to be slightly indirect. All right. And so we use the phrase indirect because the thing we want to show, we're going to actually show something else before we actually show the thing that we're interested in. All right. So I'm actually going to go, and I'm going to do this I'm going to do this nice and easy. So if I consider k plus 1 whole squared, that's going to be greater than 0. K greater than 3, greater than or equal to 3. All right. This number, and so, oh, did I want to do that? I want to do that. Sorry. And so when I expand this out, I get k squared minus 2k plus 1. And that's got to be greater than 0. So k squared plus 1 is got to be greater than 2k. And so that's going to work. No, that's not going to do it. It's not going to do what I want. I want. This is what can happen, unfortunately, when I do this. Is you go, I go k squared, and so um, maybe I should do k squared greater than 0, and therefore k squared plus 2k is greater than 2k, and k squared plus 2k plus 1 is greater than 2k plus 1. The reason I'm doing this, that's not what I want to do. I'm, 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 I don't mind doing this when it comes to revision seminars, because sometimes I want you to understand that if I come up with something I've not seen before, well, I probably have seen this before, to be quite honest, but I haven't done it. It's not something I've rehearsed because didn't know what to expect for that. This was not what I was expecting you guys to ask me about. So I was like, oh, okay, let's do this. So what happens is we try a few things. So you can see I'm going, oh, that's not going to work. That's not going to be strictly, the thing I'm looking for is a strictly true sort of statement, because what I want to be able to do is I want to replace that by this thing here so I can complete the square on it. But what could I do? Could I do k squared greater than 0, and so k squared minus 2k is greater than, no. What that's going to do is that's going to give me k plus 1 greater than 2k plus 1. And I don't want to do that. That's gone too far, because I need that. I want that to be k squared. Oh, no. Wrong game. But if I was to make that minus that, and that was minus that, and that was k squared minus 2k plus 1. We've got that. I know it's true. This is actually the other part about proving something. It's true, but what is the thing that's going to allow me to say that it's true? It's very obvious. It's fun, to be honest, especially with induction. I'm gonna see if I can figure this out quickly. That's the other thing is, of course, time pressure. Just like you have in the exam, I'm like going, oh, maybe what I can do is I can go k greater than a half. So 2k greater than 1. That's like 2k squared greater than k. I wonder if I could do, I wonder if I could do 2k minus 1 greater than 0. No, so I wanted that. I wanted to pass like that. All right, let's try a different one. Okay, greater than 2. So okay, 1 on P times K is greater than 1. Times my P. Um, hmm, let's give this another go. There's got to be an easy way to do this. Right. Oh, can I give up? I think this is where I'm going to go. I think this is one of those things where what I'm going to do is I'm going to go, hey, we could do that. But when we come down to doing this, we're going to be able to go, we are going to say that is true. All right. So if I did K is greater than 1, and so K squared is greater than K. Mm, all right, I'm going to let it go. We're going to pretend. And so this is why this is one of these things where I go, that's got to be, and so this is K squared. What I'm going to do is if I'm replacing this with something that is less than it, so we can be sure that it is K squared is equal to, so 1K and 2K plus 1 is equal to, that's 3, that's 4, that's going to be 5, that's 9, that's going to be 7. And so when we get to there, we can see that it's generally speaking true. I'm trying to avoid things that are by observation, but we're going to ignore that for the moment. We're going to do something like that. Okay, what do you do if you came across this in the exam? Well, so let's pretend this is me in the exam, because this happens to me in exams. I don't know about you. I've never actually got 100% in an exam, and that is because I have moments like this where I go, oh, there's a thing. It should be a thing. It should be an easy thing to do. I know I'm going, okay, sometimes you just state the thing that you can't do. All right. So if we're actually trying to do exams and we get to a point where we go, ooh, hey, that didn't work, then we're going, all right. The worst part about this is I'm going to see the obvious thing to do when I walk out of here, but unfortunately doing it in front of people live is terrible. All right, I'm going to let that go. What's that? Okay, those few ones. Okay, sure. So I've seen you do a lot of linear algebra stuff.
Yeah.
Seen you do
matrices. They were all in the like first half of the semester in the test. Since then we've done partial derivatives, induction.
Did you, because the induction stuff was right at the start.
Oh no, integration.
Yeah. Okay, good. So there was a whole lot of limit law. So this is from week 6 where you did limit law stuff. And so you had the definition, f is a continuous function for any real number there exists. So for any real number epsilon greater than 0, there exists a real number delta greater than 0 such that if my x is within x naught of within delta of x naught, then the f is within epsilon of x naught. So what that's saying is if I get close enough to the number, all right, I can get a function value for it. So no, you don't do it that way. So if I wanted to show, so I mean, like you could actually do that. You could. Did you do that? Was this in the mid-semester test? I think so. Maybe we won't do that. It's possible with that sort of thing that they're going to actually put it in, but this is leading up to stating functions are continuous. All right. Now, so this thing here, what we're actually going to do when it comes to talking about continuous functions is we're not going to just say function is continuous, right? If I have a theorem that says this function must be continuous, right, I rarely go to the trouble of proving it's continuous. What I do is I talk about how the function is built up. You know what? I'm showing people the wrong thing. So I'm going to change this to look at which one is this. So I'm looking at this theorem here that sort of says if I have both functions f and g are continuous at x naught, then we're saying at constant times the function is continuous. If I add the two functions, that's continuous. And so g of x is continuous. So if I was to be given, not that one, if I was to be given a function, let's say I was to be given a function that's like x squared plus 2x plus 3 on x squared plus 1 cubed. All right. Is this continuous? All right. So what I want to do is I want to go, all right, so I can go 3x, well, so 3 and x continuous functions. All right. This is going to break it down a little bit, and possibly more than we need to know. And because x times x is equal to x squared, and both x's are continuous, so I can actually break it down a bit like this. I'm doing this as a bit of an exercise in being overly cautious about how we'd go do things, right? And so then because x squared plus 2x plus 3, sum of continuous functions. And in a similar way, x squared plus 1 and hence x squared plus 1 cubed. All right. Woohoo. Okay, so what I've done is I've said both numerator and denominator is continuous, and so therefore I can say x squared plus 2x plus 3 on x squared plus 1 all cubed. So I can do a little something like that, where I actually sort of go, actually this denominator is continuous for everything greater than or for all values of x. And so this, we almost would never state that out like that, but it is actually what we would do when we're talking about showing something as continuous. Okay, so it does actually sort of, that's the sort of thought process that we're going through. It's not actually something we'd actually go to the trouble of doing. Week 6, week 7, let's have a look at week 7. Monotonic and inverse. Oh, okay. So function 2 arbitrary points, then f is called. So we've got this idea of monotonic increasing or monotonic decreasing. You'll notice that there's these fancy things where we're saying monotonic non-decreasing, which means that it can be flat or it can be increasing. So that's always a lot of fun. You'll notice the connection there. Sorry, I'm going to do this just to make sure I'm bringing people along for the ride. So I'm sort of having a flick through your notes to see if there's something that is important to be making a point of. This can be useful for when it comes to things. So there are some functions, for example, all right, a is positive, it makes it increasing, a is negative, it makes it decreasing. That would be an example of monotonic functions. This one is a monotonic increasing function, monotonic decreasing function. All right, if U and B are both, U and F are both monotonic increasing functions, then here's a so, excuse me. Monotonic, so we can actually do a thing where the composition of functions can be increasing. Inverse, let F, then the function this called inverses is called the inverse function of F when applied to. So there is if you think about what's happening, all right, every time mathematicians come up with a new thing to talk about, the first thing we do is, can we undo it? All right. So when we're talking about combining two functions, so when we add, subtract, multiply, divide, we can go, yeah, actually we can undo all of those things under the right conditions. When we come up with composition of functions, that's where we come up with a few of those technical definitions. And so I suspect we're about to get told that if f is monotonic increasing or decreasing on a domain, then its inverse is continuous over that range. All right, so basically there is an inverse exists. dx on dy is equal to the one on, so the derivative of the inverse is equal to 1 on the derivative of the actual function. That's always fun. Higher order derivatives, don't want to know about that. I can do a lot of things, but I don't know that we want to do that. That's all fun and games. First order derivatives, whether the second order derivatives also gives us information, sure. Lots of points. That's nothing. So when it comes down to like a question like this, where we're talking about a function, identify maximums, minimums of this function, identify points of global and local extrema. All right. If we were to talk about doing this, we'd go through the process of finding both first and second derivatives, and that will give us an idea of what the function is going to look like. with a lot of things like polynomials, we should have an idea about what they're going to look like. Cost functions, marginal costs. We actually we actually make some make some assumptions about some of the things we're working with, because economics is an interesting place to be, because sometimes the maths that you're doing is different from is influenced by the fact that you're trying to model, the thing you're doing is trying to be a real world situation as well. And so some of those things we observe in the real world, we're going to push onto the model in different ways. It's always a bit of fun. There is the funky elasticity. Do we want? I'm trying to find something that would be useful to be talking to you guys about. Is there something you don't feel confident doing?
Also induction and everything.
All right. So
other than that, I suppose just in most recent point, which is the last topic.
what's this?
Topic 11, integration.
Integration. All right, sure. That would be a lot of fun for everybody. I don't know about you. Partial differentiation and integration. And let's do this. Okay, so okay. I feel like all right. Integration, techniques of integration. So you've done integration by parts and integration by substitution?
Yeah, integrating by parts.
So indefinite integral, so that's what an integral means, rules of integration. So I'm just going to write these ones down here so that I've got them handy. X to the n with respect to x is equal to add 1 to the power, divide by the new power with a constant, integral of x to the minus 1 with respect to x. That would be if I add 1 to the power is equal to 0. So that's a special case. It's worth actually mentioning that one, that the special case is where my new power would be 0. E to the x with respect to x is equal to e to the x plus c. And if I do integral a to the power x, so exponential function, exponential to a different base, is going to be a to the power x, so exponential function returned, divide by ln of a. All right, so if I divided this by ln of e is just 1, so that's simple as what we've got. Okay, so I'm just going to flick through a little bit. And so there are other properties of integration, like the integral of f plus g is equal to the integral of f plus integral of g. And integral of constant times f is equal to constant times integral of f. Yes, I know you can't see that because I'm not sharing the right screen. And substitution. All right, I'm going to copy out. So this bit in the notes, this bit here in the notes, we're going to copy that bit out. So integral of f as a composed of g with respect to x times by g dashed of x dx. If I let u equal g of x, and moreover du is equal to g dashed of x dx, then this integral can be written as in f of u with respect to u. All right. So this is stating the opposite to chain rule. Woo. All right, sure. Okay. And integration by parts. Integration by parts. The integral, I don't write it the same way as they do because, all right, I'm going to swap back to this bit for a second just to show you this trick. Okay, so these are the various integral rules that you've been shown in class. So these are standard integral things. The reason I'm interested in this is you've only talked about standard polynomial type functions, log functions, and this. This is what we call substitution. All right, change of variable. This one here is integration by parts. Now you notice how I've written integral of f of g is equal to f of g minus integral of f of g. We are missing two dashes from this expression. So if I put my dash on the g up here, I put my dash on the f over here. All right, and that's integration by parts. So one of the really fun ones that I've done recently is if I do integral of, say, x to the 6 ln of x. If it makes you feel better, this is the last one of these I'm doing this year. Because honestly, I've done, this is the 5th in 3 days, so we're doing okay. All right, so we are, what happened to that pen? I've lost it, awesome. Okay, all right, doesn't matter. So what I can't, like, if I was to make this bit g dashed, none of these rules tell me what to do with integrating g dashed to get g. So I'm going to make f equal to ln of x. And that means I'm going to make my g dashed is equal to x to the power 6. And so my f dashed, I'm going to differentiate this, and we know the derivative of ln of x is just 1 on x. I'm going to integrate this, and that's going to be x to the 7 on 7. I don't need to plus c when I do that. When I get my g dash to g, I don't need to do the substitution. And so let's put this together. We are saying the integral of x to the 6 ln of x with respect to x is equal to, so f times g. So I'm going to x to the 7 on 7 ln of x minus integral. So notice minus from the thing, integral. Now, the original thing is that times that. The thing that I'm going to put over here is going to be this times this. So it's going to be 1 on x times x to the 7 on 7 with respect to x. First thing I'm going to do is simplify that expression. There's a divide by 7 thing that I'm going to put out the front. And this x is going to cancel with one of this, and this is going to be x to the 6 with respect to x. And so I'm going to get x to the 7 on 7 ln of x minus 1 on 7. This is going to be add 1 to the power, divide by the new power. Remember to add a constant of integration. So I have got, you know what, this and this is the same thing. I'm actually going to factorize this. X to the 7 on 7. And this is going to be ln of x. And this is going to be minus 1 on 7. See? Did you see that? So the key part I want to point out here is when I did this, this actually cancelled out the ln out of the expression. for that integral. So we shouldn't think about integration as a technique to solve integrals. It's a technique to rewrite the integral into a simpler form. Okay, I'm actually going to do, I'm going to try another one. So this is going to be more fun. 6. So if I talk about the integral of x, you know what? I'm going to put an n here. I'm going to go I sub n is equal to that. Does that sound like a great idea? Now, if you're paying attention, you go, no, that sounds like a terrible idea, Nick. Now, this is another situation where I have a choice, right? And so part of the point about me writing this out was to demonstrate that this is not carved in stone. Right? I can write this out. In fact, earlier today, I wrote that out and I put the dash on the other one. And I'm like, it doesn't matter. The formula is still correct. All right. Because variables, the name, it's just a placeholder. It's about making sure I do the placeholders with the dash correctly. And on one here, on the other one here. That's simple. Here, what I want to do is I want to rewrite this in a simpler form. All right. So what I'm going to do, I want to be differentiating this. So I want my f to be equal to x to the n. And I want my g to be equal to, my g dash to be equal to e to the x. So when I do my f dashed, it is equal to nx to the n minus 1. And when I do my g, just that. All right. I didn't want to make this complicated. I made it complicated, but that's okay. So my integral as a function, as dependent on n. So f times g, my formula, f times g, x to the n, e to the x minus integral. And then, so my integral is those two. This other integral is now the ones just below it. I actually did that deliberately so that I can just write that out. Okay. Do you know what? If I could actually write this as x to the n, e to the x minus n, so I can take that n out, integral x to the n minus 1, e to the x dx. But I actually have a special, I've decided to give a special notation to this thing. So I can go x to the n, e to the x minus n, I of n minus 1. Have we talked about recurrence relations before? This is what we call a recurrence relation. So we're going to go I of n is equal to x to the n, e to the x minus n, I to the n minus 1. I don't know that Yaping wants you to go that far. If you haven't seen it before, maybe not. But if I wanted to, and you know this is a thing, I could do this. I could go x to the n, e to the x minus n, and then this could be x to the n minus 1, e to the x minus n minus 1, I of n minus 2. Okay. So this is I3. This is what this is, which we are going to go x cubed e to the x minus 3 integral x squared e to the x dx, which is going to be x cubed e to the x minus 3, and then this is going to be x squared e to the x minus 2 integral of x e to the x dx, which is now going to be x cubed e to the x minus 3x squared e to the x plus 6. And then this thing is going to be x e to the x minus integral e to the x. Technically, there's a 1 there. This is going to be x cubed e, whoops, dropped off the page. Poo. X minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. Now, we should go, that is complicated, but you actually have the tools in this course to be able to do that. All right. And so there's a couple of things I'm trying to point out here. All right. This actually is connecting stuff you did in the first part where you talked about sequences, because this is actually a sequence. All right. Or possibly you could call it a series if you want to go that way. And so I can get a formula, I can get a recurrence relation for that sequence. I did remember to share the right screen, just get pause momentarily. Yeah, good. And one of the things, like, we can ask what Yaping has done a couple of months, probably about a month ago now, when he wrote the exam, was he thought about the sort of things that you will see in this course, and he's going to try and present something that you can do with the tools that has been presented, but you may not have seen before. All right. This is actually one of those things that you want to be aware of, that you can actually ask a question about what you can do without having, with the tools you have been given. What's another fun one? Okay, what else could I do that would be fun? I did that, and I did that. The other one I've seen recently, but that's a bit of fun. Integral of, what was it? Ln of x to power, I'm going to go 4 on x dx. So typically the rule is it's a substitution, right? I should try and do this as a substitution. And so I'm actually going to go, normally if I have a rational function like this, something in the numerator, something in the denominator, I let u is equal to the thing at the bottom. Ln of x is one of the few cases where I don't do that. All right, so I'm going to let u equal ln of x. And that is because du on dx is equal to 1 on x. I can write that as du is equal to dx on x. And so this integral becomes u to the power 4 du. So I'm grouping, might grab pencil. That one, that'll do. That sounds like a great plan. This bit here is going to be the du. All right. Now, this bit is really easy to solve then, because add 1 to the power, divide by the new power, so u to the power 5 on 5, add a constant integration, back substitute, so this is like ln of x to the power 5 on 5 plus c. All right, I can do things with substitutions that make my life easy. Okay, good so far? I think I've got one more trick that I think I should show you about this sort of stuff. Yep. Okay. So let's see if I can do this. So what I'm going to do is I'm going to go integral of 2x on x squared plus x plus 2 cubed. Okay. Now, so this is an example where what I want to do is I want to go u is equal to x squared plus x plus 2, and so du on dx is equal to and go 2x plus 1. All right. Make this work. I'm going to do that. All right. And this is actually what we'll do is we'll do. Can I do that? I think I'm just going to go. No, I'm going to let it go like that. I can do a clever thing, but I don't want to. I've already stuffed up enough today. I think we can walk past this one and go give it away as a bad plan. So I can do this. And so this thing is allowing me to go du is equal to the 2x plus 1 dx. And so that's that top line. And so my integral is going to become du in the numerator and u cubed in the denominator. And if I'm going to do this, I'm going to write this as u to the minus 3 dx. Add 1 to the power, makes it minus 2, divide by the new power, add a constant of integration. I'm going to write this as minus 1, so that minus sign is going to float to the top. I'm going to put this thing with a negative power in the denominator without a power. I'm going to remember to write my 2, and I'm going to put my constant integration. And then I back substitute. Okay. I've done that. Oops, 2. So I've done it that way. This is something that we will see with these rational functions. All right. Sometimes when we've got these sort of rational functions, so there's a bit of a rule that says if the numerator of my rational function is greater than my denominator, then, sorry, if the degree of my numerator is greater than the degree of my denominator, then I can do a thing where I divide it out. Did you do a polynomial division thing? Yep, good. That's what I thought. So I'm not going there. Nearly did that, and I'm like, oh no, they don't do that. So that's actually one of those things that may happen. All right. So this is like a trick that we can use if we're in trouble. All right, sure. Now, so that's some techniques in integration. Those are pretty much all the things you are going to do. All right. In sort of integration terms. The other thing you mentioned was partial derivatives. Partial derivatives. Yeah. So I mean, like, what we'll do is we'll go back to, we'll see if I can't have a bit of a peruse of the notes. So this is like if we're talking about this is, oh hey, there's the thing I did from definite integrals, fundamental theorem of calculus. Oh hey, fundamental theorem of calculus. Okay, so you did fundamental theorem of calculus, and there's rewriting things with limits of integration. And those are continuous things. So, so You actually have consumer surplus and consumer and producer surplus. All right. Have you talked about those recently? This is actually where we usually written as equilibrium price and quantity. All right, so what I will do in a second, what I'm going to do is I'm going to go back to that one. I'm going to go that one. Right. So if we do this and this, and so I have a supply curve and I have demand curve. And so I have a point here, P star, Q star. Usually I have quantity across the bottom, and I've got that the wrong way around. Please forgive me. And I have my price up here. So this is going to be the P star. And coming down here is the Q star. If we look at what's happening with my producer surplus, I needed to go demand. This is demand, and this one is supply, so that I can make it right. So if I'm doing the consumer surplus, all right, the demand curve minus, so this interval is going to calculate this value here. All right, so this is actually working out the area between two curves. We're treating P star, even though it's a constant, as a function. Yep. And so when we come to producer surplus, all right, so this is going to be this bit here. And again, we're using P star as a function, minus the supply curve. And so we're working out that area. All right. So what do we think are nice nice functions for supply and demand? Actually, I'm going to let that go because I think we've done enough integration. This would just be a case where we actually talk about splitting the integral up. So effectively, what we can do is when we do this, we can go 0, Q star, and then d of q, dq, minus integral from 0 to q star of p star dp, dq. All right, I can actually use my laws of my rules for integration to rewrite the integral in a different way. Okay, some of those things I don't think we gain a lot by talking about doing that. I think we would possibly. You do did. Hard to know what you guys done, so that's why I'm going. Differentiation, implicit derivatives. Implicit derivatives. Where's the theorem? Where's the thing I want to have? So let's just write this down here. G of x, y is equal to c. Okay, so this is like an implicit differentiation thing. Okay, so when we have a function that is expressed solely in terms of, well, as an implicit function, so there's not an explicit form for the function. So we might have something like e to the x squared plus 2y. And why don't I times by y squared? That will make it suck a lot. G of xy is equal to. Sure. All right. Going to do this. I actually got a plan in mind for this, not just because it's really difficult, but just because I want to make it really quite involved in doing this. I can't actually separate this into a function of either x or y. And so if I'm making g of x equal to some number, so some constant, I can talk about the partial of g with respect to x. All right. So because we're holding y constant, we're only really focusing on that bit. So if I talk about the e to the x squared plus 2y, I'm going to times by the partial derivative of that power. So this is a chain rule thing because there's x is in the power, it's chain rule. And I'm going to times by the derivative of the power with respect to x. Because we're differentiating with respect to x and y is held constant, this y squared out the front is still there as part of the expression. Okay, and so I can do the same thing. I can go partial of g with respect to y, but when I do that, this is now a product of functions that are dependent on y. Okay, so I've got to do the derivative of the first function, this y squared, so 2y e to the x squared plus 2y plus y, first function, derivative of this with respect to y. And so because it's an exponential function, we get the exponential function return. We times by the derivative of what's in the power, which is just 2x, which is just derivative with respect to y of what's in the power. Do you love that? I'm actually going to do a thing where I'm going to simplify. I'm going to put a y e to the x squared plus 2y out the front. And then this term will have just be 2, and this term will be plus 2y. Now, interestingly enough, once I've done that, I've gone, oh, I could have taken a factor of 2 out as well. We should never think of, like, you can do more than one step of simplification. I could have taken the exponential bit out. And so if, for this case, I wanted to work out the derivative of y with respect to x, I have got a horrible expression, but it's going to be the derivative with respect to x. So I'm going to put my 2x y squared out the front, e to the x squared plus 2y. And I'm going to divide by this one. So I might actually put the 2y e to the x squared plus 2y by 1 plus y here. Now, what do you reckon? There's a trick, isn't it? This and this are the same thing. Now, one of these cancels with one of those, and one of these cancels with one of those. This simplifies down to, all right, I can actually simplify this down to x, y. Did you see that?
You said that?
So it can happen that when we when we do this partial derivative thing to create that implicit derivative for a function, that it just simplifies. All right. There can be an unexpected simplification. All right. And so this means I could actually create the tangent line. If I was to pick a value of X and Y or a tangent. You didn't talk about tangent planes, did you? Good work. So I could just create something like this from this expression that will be nice and easy that will be an unexpected result. So I wasn't expecting that thing to happen, but it did, and it worked out quite nicely. Okay, did you talk about contour curves? In partial derivatives? When we talk about multivariable functions, sometimes we talk about contour curves as a way of visualizing or representing, and sometimes we don't. I just a little.
Not really.
Okay, let's have a bit of a look here. That was doing that. Oh, hey, there you go. Level curves. So level curves can be a useful thing to do when talking about utility. Marginal production. Okay. And so there's also so in economics, you have a lot of fun things about the marginal rate of substitution or marginal rate of technical substitution, the amount by which capital needs to be. So these things have a meaning in economics that goes beyond, because it has a actual real world context. We can actually we can put more interpretation on what these values mean. So it can be a bit differentiating systems of equations. Why would I do that? I'll find this. Oh. Oh, gotta be kidding. Oh, that is horrifying. I hadn't seen that before. Okay. So just to show people, this is actually because we have multifunction. So when we start having many functions of many variables in a system of equations, and you actually do come up with things like this. This arbitrary form, the way they're expressing that, is actually almost worse than what you would actually see. All right, so you may see endogenous and exogenous variables, and so we could find lots of these different dy on dxj sort of terms, and it all basically comes down to partial derivatives. So if you look at what we've done here, we've said f1 is function of y1, y2, up to yn. And we've said each one of those y's is a function of xj. All right. So if we simplify that down, what we're going to do is we're going to try and simplify partial. So this is like all right, I'm running out of paper. Sure. So what we're going to do is, if I have f, which is a function, thanks. Is it that? No, it's not going to do that. Let's change this one to that one. So if I have f, which is a function of y1 and y2, but I say y1 is equal to x1, is it wrong? Y1 is a function of x1 and x2, and y2 is similarly a function of x1 and x2. then what I can actually do is I can get a partial derivative of f with respect to x1. All right. And so, so I can actually, so that the way that it's expressed in the notes, brain explode, right? That is just too difficult to even get your head around. But when we do it this way, what we can do is we can do partial derivative of f with respect to y1, and then we're going to go past y1 with respect to x1, right? So this is actually what we're differentiating this. What we're saying is there's like two steps to this process. Your y1 and y2 are feeding into your process f, but both y1 and y2 depend on something else, x1 and x2. And so I want to sort of go, I can talk about how I can actually create how f will change with respect to x1 by creating this thing. And so this is literally going, well, we're going to talk about how f changes with respect to y1 and then how that would change with respect to x1. And so because f is a function of two variables, I've got to allow for how both my variables change. And so what that thing was actually trying to say is this thing is a function like we're actually saying I could in theory actually write f as just a function of x1 and x2, but it would be a very complicated function. All right. And so we might have a fairly simple sort of thing where you go, what could we do? So we could have your f, which is equal to x plus y e to the x. All right. But then I'm going to go x is equal to 2t plus s squared. And y is equal to ln of s plus t. I'm trying to keep it not too simple to be trivial, but not too complicated to be impossible. And so then what I can do is I can actually go, well, I can do my partial derivative of f with respect to t. All right. If I was a proper economist, I would actually have a context for this. And you could be going partial derivatives, poo, f with respect to y, dy with respect to t. And so partial with respect to x is going to be 1 plus y e to the x, brackets around it. Partial of this with respect to t is just going to be 2, plus partial with respect to y is just going to be e to the x, times by the derivative with respect to t is just going to be 1. Strictly speaking, what I can now do is I can go, this is going to be 2 plus 2 by ln of s plus t. Good morning, computer. E to the 2t plus s squared plus, and then e to the 2t plus s squared. All right, I can actually go to an explicit formula for this derivative in terms of s and t and leave out the x and y altogether, if I want. So this is actually one of those things that actually does happen when we're working with multiple coupled function and multiple coupled systems. And this is like the chain rule for multivariable functions. All right. So the expression you have in your notes is very difficult. Sometimes for that expression, all right, I want to write it in a simplest non-trivial form. All right. And so I could have the derivative of f with respect to, so the way I've written it here with respect to x2. And so there's a lot of different things. well, the notation to express it correctly gets very complicated quite quickly. But the actual underlying idea is I'm looking for the contribute how f changes with respect to its first variable, multiplied by how that variable changes with respect to the one I'm interested in. And this is just chain rule. But because f has two variables, I have to consider the contribution of both variables. So that's why I've done it. So if x had 5 variables, I'd have 5 terms. Each was the partial with respect to each one of f's original variables. And then each one of them would be times by how that variable changed with respect to the quantity we're interested in. And that makes it quite a difficult thing to do. But this, this is actually not too far away from something that might be asked in an exam if they wanted to test this particular thing. Okay, and it's just multivariable chain. All right, and it can be tricky, but once you've been clear about what thing is a function of what thing, and they will be in the exam, then things work out quite well. How are you going? All right, I'm going to pause here and go, do we have more questions? You're okay? Jan, have you got any questions? We could have stopped getting emails from people. Not sure if that's getting recorded, but that's okay. We're good.
Yeah.
You know, I've done a lot of these so far today. So far, so good. Yeah. I might actually end there. If you've got nothing else you want me to talk about, I'm quite happy to sort of keep going for a bit longer, but also I'm kind of out of ideas. Gonna cover a couple of things. I stuffed up one of those things at the start, and I'm okay with, I would really rather not, but this is one of those things that happens to me when I'm doing these things, but also it can happen to you while you're doing the exam. It's important to write down what you have done. Write down so you notice I said I wanted to show this, and I'm like, that was a useful thing to do, but it didn't actually help me get to the answer in the end. I'm sure when I get back to the office, I will go, oh, I should have done that. That's the thing I'm supposed to do. Yeah. It can happen to you in the exam. So if you write down what you're trying to do, the other part of that is move on. So the examiner wants to give you marks. Yupping's actually a reasonably nice guy, and he wants to see you guys do well. You have to give him reason. So if you know something about what he's asking, write it down. Write down the first step. If you don't know, like if you get asked to do a proof by induction, write down what you write down. Oh, I'd start with the proposition is I'll prove the first case. That's the easy bit. Try and then actually start down. All right, I'm going to assume it's true for K, which means this. I want to, and you can actually say, I want to show this. And that can help you work out what you're trying to show. So writing stuff down is actually one of the key things you've got to do for exam, because I can't give you marks for a blank page. I can give you marks for something that is incomplete if it is along the right path. And so that's why we want you to write down stuff. Okay. I think it's time to say thank you for your attention and your patience. I think we will call it a day there, unless you've got other questions. All right. I'm going to stop this, and then I'm going to stop the recording.